Hello everyone, welcome to the lecture 14 of the course on quantum entanglement and non-local games. Today we are going to look at the notion of states in C star algebra formalism. So far what we have done is that we had defined a quantum input game. We had also defined an embezzlement sort of a game. So we saw that if we want to achieve a fidelity of something more than 1 minus epsilon for embezzlement game, then in the limit of epsilon approaching 0, the dimensionality of the entangled state required approaches infinity. Similar was the case for winning the quantum input game with probability approaching 1. So with probability approaching 1, the dimensionality of basically the state space which they are sharing, that also approaches infinity. So the question is that that is probability of 1, success probability of 1 possible in the quantum input game. Similarly, whether fidelity of 1 is possible in the embezzlement game, right? So of course that if it is possible, then we'll need an infinite amount of entanglement or dimensionality. So but what does that mean, right? And in order to understand that, we were defining the notion of C star algebras. Now we have defined a mathematical framework, but what does it mean for for quantum states? What does it mean for quantum measurement? How do quantum states evolve under this formalism? So all those things we are going to look at now. So let's start. So firstly, an abstract state in C star algebra formalism is a linear functional S from A to C. So basically A is our algebra, the C star algebra, and corresponding to this C star algebra, we are now trying to define states. So we say that a state must be a linear functional, which means that that it is a linear function from A to C. Okay, and it has two additional properties. So we are calling this a linear function because this algebra by itself is also a vector space, and when we have like functions, linear functions from vector space to a set C, these are called as linear functionals. Now these additionally must satisfy two properties. One is that if A is an element of this algebra with A greater than or equal to 0, then S of A must be greater than 0. So note that when I say A greater than or equal to 0, we have defined the notion of positive elements, which means that basically there exists some B such that A can be written as B star B. So that we had defined earlier, right? So if A is such that A is a non-negative or a positive element, then S of A must also be greater than or equal to 0. Secondly, what we have is that S is unital. Which means that the state function evaluated at identity must be 1, right? And now we'll see that that these actually arise. So these two properties put together, they'll show that using these we'll be able to show that like if we define the measurements on state as with the measurement probability S of AK, then essentially we'll be able to get to POVM definition. So we'll just see that shortly. Now before going over there, let's see why is it even a valid definition, right? So we already have some idea of quantum states. Basically we consider them as unit vectors, but now we are writing them in a different form, right? We are saying these are linear functionals. So what does that exactly mean, right? How do those two definitions come together? So the thing is that so basically the thing is that if we look at the C star algebras which are obtained by taking subspaces of bounded Hilbert operators. So basically if we have a for any concrete C star algebra. So by concrete, what I mean is that this is essentially some subset of bounded Hilbert space, bounded operators on a Hilbert space for any concrete C star algebra. A, which is subset of bounded operators on a Hilbert space H, and any unit vector psi in H, define S from A to C as S acting on A equals psi A psi, right? So, okay, so basically, okay, let me use cursive A for the subset and let me, write it by maybe small a. So essentially the thing is that you can consider this as a measurement operator, and this is the measurement probability, right? So basically if A is a positive operator, then this is the measurement probability of measuring to A, right? So this is how we define the so basically you can consider this as the expectation of measuring A on psi. So this is like the expectation of observable A. And you can check that this is actually a linear functional, and secondly, if it is positive, if A is a positive operator, then psi A psi is also greater than or equal to 0. Now similarly for density matrices rho, we can define a corresponding state S from A to C by S of A equals trace of A times rho, right? So this also satisfies the above definition. Now moving on, we can actually now define the notion of POVM measurements. So given a C star algebra A, a POVM measurement for system A1 up to AK in A such that AI is greater than or equal to 0 and sum over K, sum over I, AI equals to identity. And a state psi and a state S, which is the linear functional from A to C, which satisfies the two properties. So applying POVM, results in an outcome I which lies between 1 to K with probabilities SA1 up to SAK. So I am leaving it as a homework exercise to show that this distribution is indeed a valid probability distribution. Show that in this case SA1 up to SAK is a valid probability distribution. Now we define a notion of reversible operations. So for quantum states, we know that the evolution of the state is through a unitary operator u. Now we'll need to define a corresponding operation which transforms these states, right? How these states evolve in time. So for that, we'll need to define the notion of an inner automorphism. Right. So we'll need to define a notion of inner automorphism as unitaries. So we have the following definition. So for a unitary u in A, so we haven't actually defined unitaries. So unitaries over here are as before are those states where u star u equals u star equals identity. Right. So for a unitary u in A, applying u to input states S, so these input states are from A to C, results in a new state S prime from A to C, where, so now this S prime is a functional, right, from A to C. So we'll have to show like how it is defined. So we already know that, okay, we already had a state S and we had the definition of S. Now we'll use that definition to define S prime as well. So this is defined as S prime of A equals S of u star A u. So for example, for S of A equals psi A psi, right, we'll have S prime of A equals psi, and then see we are, okay, so the way we have defined is that we apply u star AU to A and then we apply S. So basically this will be psi of u star AU psi. So essentially the effect is as if psi has changed to u times psi, right? So this is the overall effect. Now we can even define the notion of outer automorphisms. As reversible operations on states. Now, for a star automorphism, pi from A to A, applying pi to an input state S from A to C produces an output state S prime from A to C, where S prime of A equals S of pi A, right? So earlier what we said was that, okay, we took a specific example, we took an example of a unitary operation and then we evolved that, you know, as state A as u star AU and then we applied S. Now we are saying that we can take any automorphism. So what you can actually also check, that the previous case is also a special case of this general outer automorphisms. That is that if you have a unitary U, then U star AU is actually an automorphism. So we had already seen what is an automorphism, right? But in general, you can apply any other automorphism pi, right? Any other specific outer automorphism. So unitary operators form a special case with pi a equals U star AU. Okay. Now, one example which is not an inner automorphism but an outer automorphism is the notion of a bilateral shift of qubit. So, suppose if you have a CAR algebra and I define a bilateral shift of qubits, that will give me a notion of an outer automorphism. Bilateral shift of qubits in CAR algebra. Right, so basically what I'll do is that I'll define pi of XA ZB. So suppose if I consider A and B as strings which are indexed by Z, then I'll actually shift that entire string 1 unit to the left, and then I'll get some XA left shift, ZB left shift. So work it out. So this is also an automorphism. Next, we define the notion of a register. So a system can be said to like any abstract state. So basically when we define a register, we basically will combine all these three ideas. So first is that a system can be set to any abstract state in C star algebra. Secondly, system can be modified by applying star automorphism. And thirdly, state can be measured by applying POVM to it. Right. So we need to show what is a state. So a state is like we have already seen that it can be set to any abstract state in C star algebra, the way we have defined a state. Next we talk about how to modify. So to modify we need to apply a star automorphism, and then how to measure, then we have shown how to create this POVM. Note that in POVMs we do not define the post measurement state, we only define the probabilities of measurements. Right. So thanks a lot. Thanks for attending this lecture. In the next lecture, we look at product states and compound registers, and after that we will conclude with the perfect embezzlement strategy for the game we defined earlier. Thank you.